Hello, everyone, and welcome. Thanks for joining us today for the Avnet Silica Automotive Body Campaign. Over the next 30 minutes, we'll take a look at the industry's move toward 48-volt architectures and what that shift means for both interior and exterior lighting in today's EVs. We'll spend a bit of extra time on higher power front lighting, where this transition is having a particularly big impact. Diodes Incorporated is a global semiconductor company focused on helping customers build efficient, reliable system designs. We offer a broad portfolio spanning power management, lighting, and protection solutions, combining discrete and system-level technologies to support high performance, dependable designs across automotive applications. Diode supports a wide range of market verticals, including automotive, industrial, data center and computing, and others, by delivering high-efficiency semiconductor solutions that address today's most demanding system requirements. Underpinning this is a strong commitment to sustainability with a focus on energy-efficient products, responsible manufacturing, and reducing environmental impact across our global operations. Today we'll be focusing on Diode's automotive segment, where our solutions are designed from the ground up to meet the long-term demands of vehicle platforms. That starts with automotive-ready manufacturing and quality systems, a comprehensive AEC qualified portfolio of over 7,000 products, a hybrid manufacturing model combining advanced packaging with vertically integrated capacity for geographic balance and operational control, and finally, predictable cost and supply continuity that help OEMs and Tier 1s reduce volatility and plan with confidence. I'd like to start by introducing myself. My name is Roger Smith, and I have over 30 years of experience in automotive semiconductors, spanning system architecture, designing functionally safe automotive ECUs, including braking and body controllers, applications leadership, and go-to-market strategy. In my current role, I lead technical marketing for the Diodes Automotive segment, where I align technology, systems expertise, and market needs to drive customer value. The automotive industry is going through a major shift, driven by electrification, added functionality, and steadily increasing power demands. In today's session, we'll focus on the move toward 48-volt architectures and what that shift means for the next generation of vehicle electronics. Let's start with a few of the key drivers behind this transition. 48 volts enables significantly more power than 12 volts by reducing current, wiring losses, and copper mass. 48 volts supports electric turbochargers, e-compressors, and auxiliaries like front lighting. 48 volts serves as a cost-effective bridge between 12-volt systems and higher voltage domains. It allows the use of smaller cables, provides lower heat dissipation, and better overall efficiency. And 48-volt architectures scale across mild hybrid, full hybrid, and EV platforms, allowing extensive reuse of subsystems. Here are a few reasons why automotive lighting is no longer considered a low power load. High brightness, adaptive, and matrix lighting now push automotive lighting beyond the low power category. LED drivers, DC to DC converters, and protection now interface directly with 48 volts and higher voltage domains, not just the 12-volt rails. Lighting is now tightly integrated with ADAS and vehicle networks. It's not just a standalone load. In electrified vehicles, lighting efficiency and thermal management directly affect vehicle range. And lighting electronics now face higher voltages and transients, requiring core system level robustness. This shift introduces several new challenges for system designers as lighting moves on to the 48-volt domain. Lighting subsystems are now pushing into the 100-watt range, which brings new challenges around efficiency, heat, and packaging. As lighting connects into the 48-volt power network, designers must account for harsher transients, greater fault conditions, and stronger protection requirements. Today's lighting systems aren't standalone. They have to interact with vehicle networks for power delivery, data exchange, and diagnostics. As EVs move toward 48-volt architectures, exterior lighting splits into high-power front domain and a network rear and side domain, while interior lighting remains lower power but highly distributed. Here's a quick overview of the main lighting domains, showing how each fits into the system, what its primary role is, and the electrical and design challenges that come with it. Each lighting domain places different demands on the semiconductor content, driven by power level, functionality, and system integration. In front lighting, high power conversion, smart LED driving, fast switching MOSFETs, and robust protection with sensing and diagnostics is required. For rear and side lighting, multi-channel LED control, power distribution, protection, and you have networked diagnostics like CAN, LIN, and Ethernet. And then in interior lighting, we see more of low power, low noise LED and display drivers, along with signal conditioning and ESD protection. Here we'll look at how centralized and zonal architectures differ at the system level. In a centralized architecture, a single 48-volt powered ECU handles everything from protection and power conversion to processing, LED driving, and leveling for the front zone. This is at the cost of long harnesses, higher losses, added copper, and increased vehicle weight. In a zonal architecture, intelligence is distributed into local ECUs, shortening wiring and improving scalability and diagnostics, while still requiring careful attention to step-down efficiency, thermal performance, and transient or load dump stress. Let's take a look at two common lighting zonal architecture approaches. Here, lighting functions are grouped locally, such as in the right front zone, with only a few adjacent features, making it an early step beyond centralized body control module architectures. In a multifunction controller, in a multifunction corner controller, the ECU behaves as a local power and actuation node, supporting lighting, actuators, and sensor supplies. This is much more representative of a true zonal software-defined architecture. In practice, zonal ECUs often begin as lighting-focused nodes and expand into full corner controllers as SDV capabilities mature. In the example we'll look at today, we're going to be examining the right front zonal controller that brings together proximity-based lighting functions along with a small set of local power and safety features. We'll be breaking the block diagram down into key functional sections, and due to time constraints, focus on input protection, power management, and the LED loads. For each functional block, we'll touch on the design challenges, walk through the architecture, and highlight diode silicon solutions that address the application requirements. We'll start by looking at the challenges of implementing robust input protection when interfacing to the 48-volt power domain. In 48-volt systems, reverse battery protection must still minimize voltage drop, driving a move beyond traditional approaches toward ideal diode controllers that provide reverse protection while also serving as high side safety switches with integrated over and under voltage fault protection. With 48-volt architectures, it's not just about more power. The overall electrical stress goes up. Devices now have to handle higher energy transients, making strong transient voltage suppressors and front-end protection a requirement. At 48 volts and above, galvanic isolation is often needed to shield electronics from voltage spikes, ground shifts, and the spread of fault conditions. This table compares input protection needs in both the 12-volt environment as well as the 48-volt system. This shows higher load dump levels up to approximately 60 volts, and with VDA 320 and LV 148 requiring 70 volt survivability for 40 milliseconds, drive a practical need for 80 volt rated silicon. In the right front zonal controller, we will show both 48 and 12 volt feeds to meet ASIL fail operational goals, so a single fault cannot take out front lighting. On the 48 volt path, the large electrolytic input capacitor can drive damaging inrush current, so an isolated gate driver controls an external MOSFET to soft charge the cap through the body diode path of the second MOSFET. Once the capacitor is charged, the ideal diode controller turns on both external FETs, provided the under and over voltage thresholds are within limits to pass 48 volts safely downstream. A current sense amplifier plus an op-amp monitor the 48 volt node to support both functional and monitoring as well as safety supervision. On the 12 volt path, TVS devices handle standard transients, while an ideal diode controller provides reverse battery protection and enables the external FETs as long as safety limits are met. For 48 volt applications, the AP74700 ideal diode controller delivers minus 65 volts of reverse battery protection with a wider operating range and higher absolute maximum ratings than typical competitor devices. We're also previewing the AP74800 on our roadmap, which extends protection to plus or minus 80 volts while adding integrated reverse battery and over voltage protection. We're also showing a 12 volt ideal diode controller paired with an ultra-low RDS-on 80 volt MOSFET to reduce conduction losses and improve thermal headroom. Along with our unidirectional and bidirectional TVS and ultra-low capacitance ESD diodes for protecting power rails and high-speed in-vehicle links like CAN, LIN, and Ethernet, we're excited to introduce our newly released isolated gate driver with up to 5.7 kilovolts of galvanic isolation, high common mode transient immunity, and 4 to 6 amps of peak drive, enabling faster MOSFET transitions for lower conduction loss and improved thermal headroom. This section explores the challenges of distributing 48 volt power while maintaining clean, stable supplies for sensitive downstream electronics. Devices tied directly to the 48-volt rail must withstand 70 volts for 40 milliseconds, and Diode supports this with a broad portfolio of 80-volt and 100-volt rated solutions. Diodes has observed that select 60-volt devices with higher absolute maximum ratings can meet 48-volt stress requirements, enabling smaller footprints and lower overall BOM cost. Point of load DC to DCs and LDOs tied directly to the 48-volt rail can see significant stress. An LDO dropping a large voltage, even at modest load currents, can create thermal and efficiency challenges. Generating an intermediate rail such as 9 volts from the 48-volt bus with a DC to DC converter is a far more efficient way to support downstream LDOs that provide clean, stable supplies for noise-sensitive devices. Returning to the block diagram, the power management stage is added after input protection and must support 12-volt, 48-volt, or dual rail operation to satisfy ASIL requirements. Starting with the 12-volt domain, an ideal diode controller feeds a wide V-in buck to generate efficient intermediate rails to supply downstream point-of-load DC to DC and LDOs for generating the system and MCU supplies, while the same 12-volt source is boosted to 48 volts via the wide V-in boost to drive the 48-volt LED drivers and loads. On the 48-volt side, a 48-volt qualified buck generates an intermediate rail that feeds downstream point-of-load converters and LDOs for efficient system and MCU power, while the protected 48-volt bus directly supplies the LED drivers and loads. Looking at the power management BOM, we want to highlight our 48-volt qualified buck converter, which operates from 5.5 up to 80 volts, and in some cases up to 100-volt variants, and this delivers up to 3.5 amps in a pin-to-pin compatible device with a leading competitor and has a roadmap version of the AP6X355Q that adds a power good indicator. The diodes portfolio includes both wide V-in buck and boost converters rated up to 60 volts and designed to meet VDA 320 and LV 148 automotive requirements. A broad point of load DC to DC and LDO portfolio supports continuous loads with high efficiency, fast transient response, low noise, and high PSRR. Finally, we want to highlight a few upcoming roadmap devices, including the AP72050Q buck boost controller. This device operates from 5 volts to 55 volts with a flexible I2C interface and meets automotive cold crank and load dump requirements, as well as the AP75853 and 54Q tracking LDOs, which are designed for external sensor supplies up to 40 volts with 150 milliamps of output current capability. We'll now walk through the challenges of designing LED drivers while lighting is powered directly from the 48-volt rail. Using the 48-volt rail removes the need for a boost stage, but it comes with tougher EMC concerns and the same 70-volt 40 millisecond survivability requirement. For LED drivers tied directly to the 48-volt rail, Diodes offers 80-volt multi-topology solutions with spread spectrum technology to help manage EMC. And longer LED strings running from 48 volts increase power dissipation and junction temperature, while faster DVDT and DIDT edges also make EMI more challenging. Returning to the block diagram, we've covered the input protection and power management blocks, so let's move on to the remaining functional subsections. In the MCU processing section, Diode supports functionally safe and deterministic operation with a broad range of crystals, clock buffers, and watchdog and supervisory ICs. And while we won't dive into the details here, more information is available on our website. The input side of the ECU pulls in vehicle state and environmental data from across the car using multiple ECUs and sensor types. And Diode supports this with a broad portfolio of 48-volt ready voltage translators, amplifiers, and digital isolators, details of which are available on our website. Beyond LED drivers, the design also supports additional loads such as headlamp leveling motor control using isolated gate drivers, power MOSFETs, and Hall effect sensors, along with load switches and amplifiers for horn control, protected power for ADAS sensor modalities, and redundant fail operational support for high beam shutter actuation. For exterior lighting, we support a range of LED drivers from synchronous and asynchronous solutions for high power front, high beam, and fog lamps, to linear drivers for turn signals and side markers, LED driver controllers with external MOSFETs for daytime running lamps, and multi-chip solutions for adaptive beam forming. We're also showing a multi-phase boost controller that steps 48 volts to higher voltages for longer LED strings, along with synchronous buck and matrix controllers for precise control and actuation. The external LED driver BOM spans high power switching and linear solutions, including the AL8891Q synchronous buck rated at 65 volts and 3.5 amps. The AL886X asynchronous family operating up to 100 volts with external Schottky diodes for high power lighting loads, and the upcoming AL8865Q offers 100 volt operation at 1 ampere. For lower current functions, the AL5809 and AL5810 linear drivers support up to 60 volts and 150 milliamps, with the Roadmap SQ device extending current to 350 milliamps. The AL8866 controller drives external MOSFETs for up to 100 volts and 2 amps, while adaptive beamforming solutions combine the AL8859 multi-phase boost with upcoming synchronous buck and matrix controller devices. Let's come back to the block diagram one last time and focus on the interior lighting, where linear LED drivers support the driver compartment and footwell, and multi-channel linear drivers enable multi-zone, user-configurable ambient RGB lighting. A final look at the bill of material highlights the AL5809 and 5810 SQ family as an effective solution for map and glove box lighting, while the AL5887 multi-channel driver family provides flexible, scalable options for multi-zone ambient lighting control. For completeness, we're also including 48-volt off-rail point-of-load alternatives, such as the AP68065 and AP68105 synchronous buck regulators, which operate up to 80 volts, deliver 1 amp of continuous output current, and is pin-to-pin compatible with a well-known competitor device. This application has clear functional safety implications, as its AL rating requires that any single point failure cannot create unsafe light distribution, such as a matrix headlamp fault causing uncontrolled high beam glare. So the design incorporates multiple fail operational measures, including electric fallback to fixed low beam and a redundant protected load switch driving a mechanical backup shutter to meet FMVSS and ISO 26262 requirements. As we're beginning to wrap up our presentation, why diodes for 48 volt lighting? Diodes offers 48 volt qualified portfolio, which enables end-to-end automotive lighting and power architectures. Diode semiconductors are designed for wide 48 volt operating ranges, low dump tolerance, and low EMI performance. We support efficient 48 volt conversion, which reduces loss, wiring size, and thermal load. And we have an AEC-Q qualified system level solutions, which enable scalable lighting designs. Let's take a look at our key takeaways. So higher brightness and dynamic effects are pushing lighting loads into ranges that require efficient DC to DC conversion, robust MOSFETs, and thermal aware ICs. Lighting ICs now interface with vehicle networks, sensors, and processors, increasing the need for signal conditioning, level shifting, protection, and functional safety support. The losses in LED drivers and power stages now directly impact vehicle energy efficiency. Exposure to 48 volt domains and system level fault conditions pushes lighting designs toward higher grade silicon with proven automotive qualification and life cycle support. Thank you for spending time with us today exploring the move to 48 volts and what it means for interior and exterior EV lighting solutions. We hope this was both useful and informative, and we're glad to answer any questions you may have.